Okay, this is just a quick video to hopefully help you with this homework, because I'd really like you to be able to get through it, but it might be tricky if you haven't seen a few worked examples. Now there is one worked example in the other video that I did, but it will help you to see a couple more probably. So we'll start with the first one off the homework actually. I'll just go through part A and part B. So we've got a 10 millifarad capacitor charged to 5 volts and then discharged through a 1 kilo ohm resistor. What is the charge on the capacitor before it is discharged? So before it's discharged, it's just been charged up, and we know the voltage it's been charged up to, and we know the capacitance of the capacitor. So from that we can work out the charge, because we know that capacitance is Q over V, so Q is CV, so Q is going to be 10 times 10 to the minus 3 farads times 5 volts, which we probably don't even need a calculator for. That's going to be 5 times 10 to the minus 2 coulombs, I hope. So that's the charge on the capacitor just using the capacitance and the voltage, but then it starts discharging, and we want to know what the charge on the capacitor is after 10 seconds of discharging. So we want the formula that tells us how Q changes over time. That formula is the same format as all of them. Q equals Q naught e to the minus t on RC. And it looks like we're in luck, because we know Q naught, which is the initial charge on the capacitor. We know R, the resistor, it's being discharged through. We know C, its capacitance. And we know T, the time. So we know everything. So literally all we have to do is just plug everything into this formula. So Q naught is 5 times 10 to the minus 2, which is 0.05 coulombs. I might actually write it out like that. Might be neater, might not, we'll see. So it's 0.05 coulombs times e to the minus, t is 10 seconds, divided by r, which is 10 to the 3 ohms, because it's kilo ohms, times the capacitance, which is 10 times 10 to the minus 3. Now, depending on what your maths is like, if we look at this exponent up here, actually a whole load of this cancels out, because we've got the 10 to the 3 times by the 10 to the minus 3, which cancels out, and then we've got the 10 divided by 10, which cancels out. I mean, you're more than welcome to put that into your calculator, but I'm pretty sure it just works out as 0.05 times e to the minus 1. Now, to work that out, you probably are going to want your calculator. You might be able to do it without, but we'll use a calculator. So I'm going to do 0.05 times oh, can I even see where it is on this? I'm looking for ln, or e to the something, and I can't actually see. Here we go. Ln is here and e to the something is there, so I'm going to go shift e to the something, and it's e to the power of minus 1. So I want 0.05 coulombs times e to the power of minus 1. Your calculator might not look exactly like this, but it should have an e to the x or an e to the something function. So we want e to the power of minus 1 equals, we'll call that 0.018 coulombs. So after 10 seconds, the charge has gone from 0.05 coulombs to 0.018 coulombs. This answer here, well, I'm just thinking about sig fig. This quantity is only to 1 sig fig, this quantity is to 2, so 1 or 2 sig fig is fine for this. So anyway, this one was quite straightforward. We just had to plug everything into the formula, and hopefully that answer is correct. Let me know if it's not. Now the other one, which was the example I gave at the end of the video, is less straightforward. So let's take a look at it. Okay, so a 560 microfarad capacitor is charged to 5.5 volts and then discharged through a resistor. Initially a current of 10 milliamps flows. What is the resistance of the resistor? Well, for resistors we can use V equals I R, therefore R equals V over I. What we need though for this is a V and an I from the same time, because if we've got V's and I's at different times, that's not going to help us. We need V and I at the same time. Luckily for us, we know we've got an initial current of 10 milliamps, and we know that initially it's charged to 5.5. So these are both the initial values. So we know the initial voltage and the initial current. Since they're both at the same time, that enables us to work out the resistance. So then R is going to be, if we take the initial voltage, 5.5 volts over 10 milliamps. So that's 10 times 10 to the minus 3 amps. What can we do with these powers of 10? 10 times 10 to the minus 3, that's like 10 to the minus 2. And if we're dividing it by 10 to the minus 2, that's like timesing by 10 to the 2. So that should be hopefully 550 ohms. So we've got the resistance, and that's going to remain constant for the rest of the time. Now, how long does it take for the current to fall to 5 milliamps? Well, we've got our formula, which is the same format for all of them. I equals I naught e to the minus t over RC, and we want to know t, the time, which is a bit of a nightmare because it's stuck up here in this power of E, where it's quite hard to get at. So the way I'm going to do it is by rearranging everything first and then plugging the numbers in, but you're welcome to take whatever approach you like. So what I'm going to do is divide both sides by I naught. So I on I naught equals e to the minus t over RC, and what I'm going to do then is take the natural log, the ln, of both sides. Now if you do maths this will be easy. If you don't do maths then just pay attention. So ln I over I naught equals ln of e to the minus t on RC. But by definition, if you take ln of e to the something, you just get back the something, okay, which simplifies that entirely. So this means that ln I over I naught is just going to be minus t over RC. So we're not a million miles away now. We've just got to get our t on its own. So we've got to take the minus sign over to the other side and multiply both sides by RC. So RC, or minus, sorry, RC ln I over I naught equals t. And then all we've got to do is substitute in the numbers. So R, I believe, was 550 ohms times capacitance, totally forgotten what that was, 560 microfarads, 560 times 10 to the minus 6 farads, times ln of the current we're interested in is 5 milliamps and the initial current was 10. So 5 milliamps over 10 milliamps. Notice that these two units cancel out. So it wouldn't actually matter if I'd converted them both to amps or if I leave them both in milliamps. It turns out here they cancel out, and ln of 5 over 10 is going to be ln of a half. Anyway, let's whack all this into a calculator and see where it gets us. So minus, what's all this? Clear. Minus 550 times 560 times 10 to the minus 6 times ln of 5 over 10 close brackets equals 0.21 seconds apparently. So it's going to take 0.21 seconds for the current to halve from 10 milliamps to 5 milliamps. So these questions, they just need practice basically, and if you don't do maths, then learning both sides and then doing this bit here where the ln of all that is just the that, all of that takes practice, and the only way to get good at it is to do it lots of times and practice it with lots of different questions that are all asked in a slightly different way. But see how you get on. Hopefully I haven't made any mistakes in this. If I have, let me know. And hand the homework in on Thursday morning. Excellent.